Welcome to the Deep Dive.
Great to be here.
Today we're tackling something really fascinating, a geometric paradox that honestly kind of bends your brain a bit. Prince Rupert's cube.
Ah, yes, a classic.
The basic idea is, well, imagine cutting a hole in a cube,
Okay.
but somehow a larger cube can pass right through that hole.
Okay.
Sounds completely impossible, doesn't it?
It really does, and that's exactly why it's so interesting. It forces you to question, your basic assumptions about space and shapes.
Right.
And it's not just how it works, but the story behind it, the history, and the fact that people are still exploring related ideas even now.
Okay, let's dig into that history. Where does this start? I read something about a prince and a wager.
That's right. It goes back to 1693, Prince Rupert of the Rhine.
Okay.
According to John Wallis, the mathematician, the prince basically made a bet.
A bet about cubes.
Yeah. Could you cut a hole through a standard cube, let's say a unit cube, side length, a hole big enough for another cube of the exact same size to pass through?
Even that sounds tricky, like threading a needle perfectly.
Exactly. And Wallis confirmed it was possible. He worked out a way.
So the prince won his bet.
He did. Wallis's initial calculation showed a cube that was just slightly larger, maybe 1.035 times the size, could pass through.
Still impressive, but not quite the paradox yet.
Not the full paradox. That came about a century later with Peter Newland.
Okay, what did Newland find?
He found the optimal solution, the absolute biggest cube that could possibly pass through our unit cube. And get this, its side length is about 1.06.
Wait, 1.06, so 6% larger than the cube it's passing through.
Precisely. 6% larger. That's the real kicker. It's not just same size, it's bigger.
Okay, my intuition is officially broken now. Physically, how does that work? Is the hole shaped really weirdly?
It is. It's not like drilling a simple round or square hole straight through, face to face.
Right, that wouldn't work.
No, think about angling the passage. You're essentially carving a tunnel diagonally through the cube's interior.
Ah, okay. So exploiting the diagonal length.
Sort of. Imagine placing 4 specific points inside the cube, 2 on adjacent top edges, and 2 mirrored on opposite bottom edges.
Okay, I'm visualizing.
Each point is 34 of the way along its edge from their shared corner. These 4 points define a square.
A tilted square inside the cube.
Exactly. And if you extrude that square, basically push it through perpendicularly, that forms the passage.
And the side length of that specific square allows the bigger cube.
Yes, the side length of that tilted square works out to be exactly 3 times the square root of 2 divided by 4, which is about 1.06066.
Wow. Okay, so it's pure geometry and finding that perfect non-intuitive angle.
That's the essence of it. Precise angle, precise dimensions.
Now, building one of these sounds incredibly difficult, especially back then.
Oh, absolutely. For that maximum 1.06 cube, the whole leaves the original cube incredibly fragile.
Like barely holding together.
Pretty much, just thin connections at the corners. So for centuries, it was more of a theoretical curiosity. Possible mathematically, but, practically impossible to make a sturdy model.
Right.
But now, well, things have changed.
3D printing.
Exactly. 3D printing makes it relatively easy to create quite accurate physical models. You can actually hold this paradox in your hands now.
That's cool. It really helps visualize it. So is this cube thing unique, or do other shapes have this Rupert property?
Great question. And no, it's not unique to cubes. Many other convex polyhedra, solid shapes with flat faces.
Pyramids, dodecahedrons.
Yes, those. They also have the Rupert property, all 5 platonic solids, for instance. A tetrahedron can pass through a hole in another tetrahedron.
I never would have guessed.
And it's an active area of research, which is fascinating. People are still exploring the boundaries of this.
Really? Like what?
Well, there was a very recent preprint, I think from August 2025, by Steininger and Yurkiewicz. They claim to have found a counterexample, a convex polyhedron that doesn't have the Rupert property. They even gave it a name.
Which is?
The noprosedron.
Huh. Okay, clever. So a shape that can't have a copy pass through itself.
Apparently so. It just shows that even in classical geometry, there are still discoveries, still open questions. And this extends, by the way, to higher dimensions, too. Hypercubes have the Rupert property.
Mind-boggling. So from a 17th century wager to potentially brand new geometric discoveries in higher dimensions, Prince Rupert's cube is quite the journey.
It really is. It's a perfect example of how mathematics challenges our intuition and reveals hidden structures.
It definitely makes you reconsider what seems obvious about space.
Absolutely. And that's maybe the key takeaway. Question the obvious, look deeper. So a thought for you to take away. Where else, maybe in science or even just everyday life, might things that seem impossible actually be true if you just find the right way to look at them, the right angle?
Hmm, that's a great question to ponder. Thanks for this fascinating deep dive.
My pleasure. It's a fun one.